Our next integration method is called integration by parts, and it's all about splitting fractions up into smaller fractions so that the integral becomes integrable. So here's our first integral, an integral of 2x plus 3 over x squared plus x minus 2 dx. Now it may be possible to integrate this by a different method. I haven't really explored this one. I suspect we could probably find another way to integrate this. But I'll show you the integration by parts, which I think you'll find is pretty straightforward and easy on this one. And so, first of all, I want to factor my denominator. Now, if you can't factor the denominator, that could be a problem. And we'll address that later. So, but anyway, this one becomes the integral of 2x plus 3 over x plus 2 and then x minus 1 dx. Alright, so I factor the denominator. And over here I'm going to do my side work. I'm going to take this fraction, 2x plus 3 over x plus 2, x minus 1. And I'm going to set it equal to a over x plus 2 plus b over x minus 1. So this is a purely algebraic technique to break up this fraction into the sum of two fractions. And as you can see, if we add these fractions together, we would get a common denominator of x plus 2, x minus 1. So it makes sense to go backwards and split it up. Okay, well, there are two very reasonable techniques for solving this for a and b. And then, of course, once we have a and b, we just break up the integral, and each of these will integrate very nicely. But the first method is called equating coefficients. So let me write that word down, equating coefficients. And I'll show you what that means. Now, I think most of the time when you do these problems, you'll like our other method. That's not equating coefficients. I forgot what it's called. Maybe I'll think of it while I'm videoing these. But equating coefficients, we'll do it this way. First of all, I'm going to clear the fractions. I'm going to multiply everything by my common denominator, x plus 2, x minus 1. And as you can see on the left side, the denominator cancels. So I'm left with just my numerator. 2x plus 3 equals, over here the x plus 2's cancel, so I have a times x minus 1. And then the b's cancel, the x minus 1's cancel over here, so b times x plus 2. So I'm going to continue the algebra here. Ax minus a plus bx plus 2b. And at the end, I'm going to factor x out of these two terms. So I have a plus b, parentheses x. And then my constant terms are negative a plus 2b. Alright, so here's where it gets its name, equating coefficients, because the only way that 2x plus 3 can equal to this polynomial is if a plus b equals to the coefficient of x, 2, and negative a plus 2b equals the 3 coefficient. So I'll write that up over here. I have a plus b equals to 2. And then negative a plus 2b equals to 3. Negative a plus 2b equals to 3. So I have a little system of equations to solve. And it may have been a little while since you solved these. This happens to be a very easy one because if I just add these equations together, the a's cancel off. So I end up with 3b equals to 5. So b was equal to 5/3. Now if b is equal to 5/3, I could substitute up to here. A plus 5/3 equals to 2. And then subtract 5/3. Well, 2 is 6/3, so a is going to end up being 1/3. A is 1/3. Alright, so let me, as you can see, I have a small board, so I'm going to cheat on my room here. I'm going to put a equals to 1/3 and b equals to 5/3 up on top here. All right. Now then, I want to show you the other method, and like I said, I don't recall its name, if it has a name, but we'll still clear the fractions and come down to this point. So I'm going to erase everything below it and to the right here. And I think in most cases you'll probably find this second way to be a little easier or a little quicker. Here's the idea. If I let x equal to 1 in this equation, this will disappear. I have a times 0. So the a term disappears and I can solve for b. So if I let x equal to 1, then on the left side I've got 2 plus 3. I have 2 plus 3 equals to a times 0 plus, and I have 1 plus 2 is 3, 3 times b. So that term cancels, and as you can see I have 5 here, so b is equal to 5/3. Alright, so that matched what we got earlier a minute ago. And then, so hopefully you got this down. I'm going to erase this part and do the other one, because if I now let x be -2, I'll be able to solve for a. So when x is -2, I get 3 minus 4, that'll be a -1, equals to, and here I've got a times -2 minus 1 is -3, -3a, and then over here the minus 2's cancel, so I have 0b. I'll leave b off. As you can see here, solve for a would be -1 over -3, which reduces to 1/3. Alright, so of course it worked out, and but those are the two main techniques. Now, some of these problems are complicated enough, you may want to do a partial blend of both, equating coefficients and also canceling terms to solve for a letter. So, alright, well, we'll take this result and finish the integral. So now I get to erase all this. This next step is a little bit of taste or style. This time I decided to split this into 2 separate integrals. And recall that we had a over x plus 2, well, a was 1/3. So I'm integrating 1/3 dx over x plus 2. And then here's b plus 5/3 integral dx over x minus 1. Now these forms are natural logs. Recall that the integral of dx over x is the natural log function of x, and we find it's necessary in general to put absolute value bars over that around the inside there. That makes a difference, in particular when you plug in limits of integration and you end up with negative numbers in here. It works out with the absolute values. So that's probably a discussion you saw somewhat earlier with natural logarithms. So what happens when I integrate dx over x plus 2? Well, if I did a real simple u substitution, if I let u equal to x plus 2, then du is equal to dx. So I'm integrating here du over u. It becomes the natural log of u, which is the natural log of x plus 2. So if you want to take a little look at that, it's not a bad idea. But the good news is that when you're in the logarithmic form, dx over a linear factor, so I'll call that a linear term or linear factor. If the coefficient is 1, then the antiderivative will be the natural log of the denominator. Now if I had a 2 or a 7 or something else here, then we would have to do some fiddling around to get that right, but it makes it easy when we have 1x plus or minus a constant number. Alright, same over here, 5/3 natural log, absolute value of x minus 1, and then we have a plus c out there. And now there's a few ways we could go here. I'm going to factor out the 1/3. I think I'll just keep the 1/3 out. And I can combine the logarithms together. So this would become absolute value, parentheses, x plus 2 times x minus 1 to the 5th power. And so that combines two rules of logarithms. The sum of two logs is the logarithm of their product. And I factor the third out. 5 times the logarithm is the logarithm to the 5th power. So there's a power rule that allows this 5 to go up here. There it is. And this became a multiplication because we were adding logarithms together. So just a little quick review of rules of logarithms. And I think that's a pretty good answer for that one. So, all right, well, let's go on to another example. We'll complicate these a little bit as we move along. The techniques of integration by parts can get more complicated. And notice here I have a third power of a term, and that leads to its own technique. When you have a power of a factor, then we have to use a little different approach. And another one is, later we'll see another example, what happens when you have a quadratic down here, like a x squared plus x plus 1, that cannot be reduced, cannot be factored. Cannot be factored. How do you handle that? Okay, so there are some flies in the ointment, as it were. Now I'm going to, I'll show you how to work this. I'll have, let's take the fraction, x cubed minus 2x plus 5 over x cubed 3x plus 1. All right, now it turns out, let me just write out what you do on this one. I'm going to make it a over x plus b over x squared plus c over x to the third power plus d over 3x plus 1. So I can't think of a real cosmic reason why we should split this up this way. Okay, but it does work. It does work. And so I tell my classes, I think probably some of this stuff is just figured out by trial and error, and then people eventually see patterns and they prove theorems. And but when you have a power of more than one, like a third power, then you've got to repeat that factor in the first power up to, in this case, the third power. So that's why I have x squared, and x cubed. If this was x squared, I would only do the first two terms. All right. So it turns out this works. And then also I took the 3x plus 1 and put it over here by itself. All right, now we clear the fractions. I'll multiply by x cubed times 3x plus 1. And so a little bit of algebra there. And I think you'll get used to this algebra very quickly if you don't immediately see it. When I multiply through, this entire denominator cancels. So I have x to the third minus 2x plus 5 equals, here x cancels, gives me x squared. So I have a x squared, 3x plus 1. And then here I get bx times 3x plus 1 plus c times 3x plus 1, because all the x cubes cancel. And then d x to the third power. So it would be perfectly fine to multiply all this out and equate coefficients. Now when you do that, we have 4 letters. So A, B, C, and D, we're going to end up with a system of 4 equations. And I don't think it would be bad at all to solve that for this problem. Generally, a system of 4 equations is, if it's really filled out, it's pretty tough. And we have techniques of linear algebra we use, or maybe your calculator can work these out very nicely. But here I'm going to do a blend of, or at least I'm going to start off by canceling some of these here to solve for letters. So let's see how it works. Now to me the easy one is to let x equal to 0. So if I let x equal to 0, on the left side I've got 5. 5 equals 2. That's going to give me a 0. That'll give me a 0. This will give me a 0. But I do have a c term. So I have c times 0 plus 1. So there you go. C equals to 5. That's 1 down. Okay. one term down. Another easy one to figure out would be what if what if you pick the number that cancels this factor? Then that will give us letter D. And this would have to be negative 1/3, wouldn't it? Because if you solve 3x plus 1 equal to 0, x is going to be minus 1/3. Well, let's do that over here. X equals to minus 1/3. And so that will cancel this term, that term, and that term, and I'll have D. So, but over here it's going to get ugly. Put minus 1/3 in here, cube it, I get minus 1/27, then plus 2/3 plus 5 equals to negative D over 27, so that's x cubed is minus 1/27. That's, like we said, that's going to be a little ugly. Let's go ahead and multiply by 27 to see what we get. So I end up with minus 1 plus 2/3 of 27 would be 18. 5 times 27 is 135. And this will be minus D. So D is going to be the opposite sign of this. Let's see, 135 plus 17 is 152. So D is going to be negative 152. Alright, so let's see, 18, 40, 53, 152. That's right. D is negative 152. Alright, well that's what happens when you make up these problems on the fly. You tend to get some pretty wild answers sometimes. Okay, so let's go from there. Now I think I'm in a small bit of trouble here, and I'm probably going to have to go find my calculator, because in order to get A and B, I have no way to cancel off 3 of these other factors and just, for example, leave A. I can't think of a way to do that. I don't think there is a way to do that. So I am going to have to, in a way, equate coefficients. And unfortunately, D is really large, isn't it? So let me get my let me take a time out and get my calculator. I'm going to need it. I'm back, and if you hear a little noise in the background, that's my furnace next door. It's kind of loud, but I got the door shut, so we'll see what happens. Okay, earlier I let x equal 0, and that gave me c equals to 5. I let x equal minus 1/3, and I got negative 152 for D. Let's let x equal to 1. I want to pick a friendly number here. So if x equals to 1, I get 1 minus 2 plus 5. So that's 5, 6, minus 2 is 4. 4 on the left side equals to, plug 1 into here, I've got a times 1 times 4, so 4a. And then here I've got 1 times 4, 4b, plus, put 1 into here, I've got 4c, plus d. Okay. Now, we know what c and d are, so I'm going to plug those numbers in. I end up with 4 equals to 4a plus 4b plus, okay, 4 times 5 is 20, minus 152. And then, let's see, let's bring that over and subtract 20. Let's see, 156, 136 equals to 4a plus 4b. And if I divide by 4, this will be, what will it be, 25, 34? I'll make sure, because there's really nothing worse than messing up the arithmetic on one of these problems and having to reshoot a video. Alright, so I have 34 equals to, and here I got a plus b. So we know what a plus b is, equals to 34. Alright, so what happened was I plugged the number in, I ended up with all 4 letters, but I already know what 2 letters equal. So that gives us an equation with just a and b in it. I need one more equation with a and b in order to finish my problem, to get a and b, because we need 2 equations to solve for 2 letters. So I'm going to erase most of this, and what number should I plug in now? And I'm thinking about plugging in minus 1, because I want to stick to small numbers. And if you can. So let's make this x equal to negative 1. Alright. So here I've got minus 1, plus 2 is 1, 1 plus 5 is 6. So 6 equals to, double check myself, 4, 6, that's right. If I plug in minus 1 here, I've got 1 minus 3 is negative 2 times 1, I have negative 2a. Put minus 1 over here, I've got negative 2 times negative 1 is positive 2b. So minus 2a plus 2b. And then negative 2c minus 2c. And then this will be negative, so that'll be minus d. Okay. So now use these results from earlier, and let's see, I've got 6 equals minus 2a plus 2b, minus 2 times 5, that's minus 10, and then minus d is going to be plus 152. And what do we have now? This is 142. 6 minus 142 is minus 136. Is that right? Yes, it is. Equals minus 2a plus 2b. And if I divide by 2, I get negative, what would that be? 68? Minus 68? Yep, I think so. Minus 68 equals to minus a plus b. Okay, so I was able to generate a second equation with a and b. Crossing my fingers that I have not messed up the arithmetic. And but you won't find out because I'll just have to reshoot the video, won't I? All right. So if and look how nice this is. This seems to happen a lot. Not every time, but seems to happen a lot. If I just add these equations, the a's cancel. I get a negative 34 equals to 2b. So b is going to be half of that, negative 17. B equals to minus 17. And then if b is minus 17, if I add that over here, I get, what do I get, 51? I think so. Yeah, a is equal to 51. There we go. So, we have it. All the coefficients, hopefully very accurately. So, was that the easiest way to do it? I might have multiplied all this out, equated coefficients. I would have had 4 equations with 4 letters, and then I would have solved it on my TI-86. So that would have been a practical way to do it. Some calculators will solve systems of equations really nicely. If you don't have a simultaneous menu button or something, if you have matrices on your calculator, you can learn how to solve those, but you'd have to learn something about linear algebra. So anyway, to me, without using the big guns of a calculator like that, this is probably the most efficient way to solve this particular problem. Well, I need to incorporate that up here so we can finish our problem. And so this is equal to, a was 51, so I have 51 integral. So I have 51 over x, I'm going to write that as dx over x. And then b was minus 17 integral. And here it's over x squared, so let me make that x to the negative 2 power dx. And then I have to erase, don't I? Okay. So let's see. C over x cubed was next. And c was 5, so plus 5 integral x to the negative 3 dx. So I've written it this way, so it's easier to integrate, find that antiderivative. And finally, d was minus 152. So minus 152 integral of dx over 3x plus 1. All right, so there's my integration, and it doesn't look too tough to me. I think there's a little a little trick over here we have to be careful about, and we'll talk about that. That's why I threw in a 3x plus 1. I wanted to have one of these integrals in it. Alright, so this is the logarithm form. So we have at least one logarithm. I think we'll have actually 2 logarithms. So this gives us 51 natural log absolute value of x. Here, when I integrate, I'm going to get x to the minus 1 over negative 1. And so the minus 17 x to the negative 2 dx will be minus 17 x to the minus 1 over negative 1. You see the negatives will cancel, and this becomes 1 over x. So I have plus 17 over x when we get done with that one. Likewise over here, we're going to end up with x to the minus 2 over negative 2. And so I'll be minus 5 over 2x squared when we integrate that one. What about this one? Well, if I factored out the denominator 3, I could do it. Let me just take a shot at this. I think this is going to be minus 152 over 3 natural log absolute value 3x plus 1. So let's double check that, because if you take this derivative, you'll take the derivative of the log, will be 1 divided by 3x plus 1. But then the chain rule means that you multiply by 3. And so I need that 3 to cancel here. Okay, so that's why I knew to put this as 152 over 3, because going backwards with the derivative means the chain rule, I end up with a straight 3 out here that needs to cancel off. And all right, well, that's a bit on the ugly side, isn't it? I might be inclined to just leave it like that. And but we could. The only thing we can, well, we could combine these terms if we were determined. We could combine these together. We need common denominators and that sort of thing. Let's see. If I put this over 3 times 51 by coincidence is almost 152. It's actually 153, isn't it? So if I factor out 1/3, I end up with natural log of x to the 153rd power over 3x plus 1 to the 152nd power, and this other stuff. I really think that's a bad idea, okay? Because now you have terms that are raised to really humongous powers. I just think that's probably a bad idea. So let's just keep the answer this way. I think this is because of the large coefficients, we don't want to raise those logarithms to those very large powers, and we'll just keep it that way. So I think I'll stop on this one, and I'll cook up another good one for you. Here's the third type of partial fraction integration. We're integrating dx over x plus 1 times x squared plus 1. Now, what's different is that the x squared plus 1 is called an irreducible quadratic. That just means it can't be factored. And at least it can't be factored over the real numbers. Okay. Now, x squared plus 1 actually can be factored. In case you're wondering about that, it would be factored as x minus I times x plus I. And using the complex number I. And that unfortunately opens a can of worms. We haven't studied that kind of math, integrating with complex numbers, and it's got a little more complexity to it than you might imagine. So we stay away from that in ordinary calculus and worry about complex numbers somewhere else upline. So let's don't go down this path. And but there's a way to work this problem, nevertheless. When we do the partial fraction expansion, I'm going to set up this way. I have 1 over the linear factor, x plus 1, and then x squared plus 1 is the quadratic factor, the irreducible quadratic factor. And now this part will be rather ordinary. I'll put a over x plus 1. For the x squared plus 1, I'm going to write bx plus c over x squared plus 1. Alright, well, if you if you don't do this, so notice that the bx plus c is a first degree polynomial. Here's a second degree polynomial, there's a first degree polynomial. And well, why does this work? Well, let me try an alternate form. If I said this was equal to just a over x plus 1 plus b over x squared plus 1, then when we go to add these fractions together, rather than worry about solving for a and b first, if I add these together, I'm going to get a parentheses x squared plus 1 plus b parentheses x plus 1 over this. And you can, right away you can see the problem, because ax squared is the only x squared term here. And since there's no x squared on top of my fraction over here, then a would have to be 0. If that's 0, then I'm missing this term. And then you end up with b over x squared plus 1. So with a being 0, that cancels. And then this would cancel. And a constant over x squared plus 1 does not take you back to the original. So there's a quick explanation why we can't get away with just putting a constant on top of our irreducible quadratic. So we try this route, and let's go ahead and clear the fractions. So like usual, I'm going to multiply everything by the common denominator. And this cancels, leaving 1 equals a, that cancels, x squared plus 1 plus this canceled, so I have bx plus c times x plus 1. And here I'm going to go ahead and multiply this out. Ax squared plus a plus bx squared plus bx plus cx plus c. And so if we equate the coefficients, the x squared terms are a plus b, times x squared, and the x terms are b plus c times x, and then the constant terms would be a plus c. A plus c. Okay. All right. Well, I'm running out of board space. This, in equating the coefficients, over on the left I have 0x squared, so that a plus b is 0. I have 0x, so b plus c is 0. And the constant 1 is a plus c. So let me see if I can squeeze these in down here. I've got a plus b equals 0. And b plus c equals 0. And a plus c equals to 1. All right, well, what do I do if I subtract these equations? The b's will cancel, so I get a minus c equals 0 minus 0. So a equals to c. If a equals to c, then this will be 2a equals 1. So a will be 1/2 and c will be 1/2. And then if c is 1/2, b must cancel it to get 0. So over here, or same with a, then b is going to have to be negative 1/2. There we go. All right, well, so when I rewrite this up here in my integration, a, b, and c all have halves in them. So I'm just going to factor out 1/2. And I have the integral of 1 over x plus 1. And then plus bx plus c would be negative x plus 1. I'm going to, I tell you what, rather than have a negative x plus 1, I'm going to make this a minus. And then I have x minus 1 over x squared plus 1. There we go. All right. So I think everything works out here because the b was a minus 1/2. So I do get minus 1/2 b, and then positive 1 times a half. C is 1/2. All right, so that looks correct. Now, before I finish this integration, I want to show you another way you can think about this problem. And I'm going to go erase all this stuff here. I'm going to show you an alternate way to get a, b, and c, where we actually do get to use the complex number I in a productive way. So let's erase this. And first I would start off by letting x equal -1. So if x is -1, then I have 1 equals to, this will be 2a, 1 plus 1, 2a. And this -1 plus 1 is 0. I don't care what that is. That's all 0. So this tells us that a is positive 1/2. All right, so that's one thing down. And if I let x equal to letter I, okay, so you would have to remember here that I is the square root of -1. I squared is defined to be -1. So actually those are both definitions introducing complex numbers. And so I squared is always defined to be -1. Which means when I put I here, I get I squared plus 1. -1 plus 1 is 0. So the root of this equation is I. So when I plug all that in, then 1 will equal to 0. This cancels, 0. I have b I plus c times I plus 1. You might think, well, what good did that do us? Well, let's multiply it out. 1 equals to b I squared plus bi plus ci plus c. And this part here becomes a negative b, because we want to change I squared to -1. So in terms of numbers here, 1 would equal to b plus c multiplying I, and then the constant would be c minus b. Well, on the left, this is 0i plus 1. So to equate 1 with this complex number, the imaginary part of the problem is 0i, and so b plus c equals 0. And the constant number, the real part, c minus b equals to 1. C minus b equals to 1. If we add those equations, b cancels, I get 2c equals to 1. C is 1/2, just like before. And then over here, you can figure out what b has to be. B has to be -1/2. So sometimes that works pretty handily using complex numbers. I'm thinking of some more complicated ones I've done in another course called differential equations, where we actually do get to use complex numbers somewhat. So anyway, so this is an alternate way of getting your coefficients. I don't know if you want to go down that path, but that you can do. Well, I'm going to erase everything from here on down and finish this integration. Now we run into an immediate stumble here, because how are we going to integrate this part? X minus 1 over x squared plus 1. If I try to u substitution technique, if I let u be the denominator, x squared plus 1, the derivative is going to be 2x. Well, my numerator is not a multiple of 2x, it's x minus 1. So that a u substitution is not going to work there. But really there is a kind of simple way to resolve this. I can split this up into two fractions. So let's go ahead and do that. 1/2, and I'll put a bracket. We're going to integrate dx over x plus 1. So I'm just going to take this out separately. That's the first integral. Then minus integral x over x squared plus 1 dx. And then this will be a plus integral of dx over x squared plus 1. So that allowed us to split this fraction up. I have minus x over the denominator, and then I have a positive 1 over the denominator. And then we'll approach these separately. The first one is the logarithmic form. So it's going to be natural log, absolute value of x plus 1. Over here, easier than it looks, because now we're okay. The derivative of the denominator is 2x. That's 1x. So let me put a 2 here and a 1/2 there. And it turns out that this is a logarithmic form, because I have I'll write it down here. When you integrate 2x, x squared plus 1 dx, this is the integral of the differential of x squared plus 1 over x squared plus 1. So we have the d something over something fraction, and this is the logarithm form. So this is going to be a logarithm of x squared plus 1. So we have minus 1/2 natural log x squared plus 1. So again, you can check yourself, ignoring this 1/2 in front, just look at this part of it. This derivative is going to be 1 divided by x squared plus 1 times the derivative of x squared plus 1, which is 2x, using the chain rule. So it works out rather nicely. What about that last integration? Do you recognize it? Well, that's the inverse tangent. dx over x squared plus 1 will be the inverse tangent of x. And then along the way we have a plus c to add there. Alright, well, let's try to consolidate this a little bit. If I, let's put everything over 2, okay, so 2 over 2, 2 over 2. So that way I can factor out my denominator 2, which makes it a 1/4. I have 1/4 inside. I'm going to, not ignoring these denominators now because I factored out the 2's. But up here I have a 2. This makes it x plus 1 squared. So natural log x plus 1 squared. And then divided, because we're subtracting the logarithm, we can divide within a single logarithm, x squared plus 1. And then plus 2 inverse tangent of x plus c. So I was able to take out the absolute value bars here, because when you square it, it's going to come out positive anyway. So we don't have to worry about the absolute value here. And x squared plus 1 is always positive. That's why I never put absolute values bars on that one. So there it is. Presumably this derivative will eventually lead you back to that fraction. So now we as you've seen so far, we tend to, in these partial fraction problems, we tend to get logarithms. We tend to get terms where x is raised to a negative power, like it might be like 1 over x, or 1 over x squared, or 1 over x cubed. Or we also tend to find inverse tangents a lot. Now I don't recall if those are the only 3 types of results from integration by parts. There may be some other exceptions I don't know about, but I can't think of. But anyway, these are pretty common to see these types of functions show up between this problem and the last one we did. So, okay, well, I have kind of introduced the basics of this. I'm going to, my next video is going to be a recap video, and then I'm going to show you some other problems after that are kind of interesting. So let me do a quick recap video on this. One textbook I have lists 4 different cases for partial fractions, and so I thought we'll go through those 4 different cases, and then we'll look at something that's outside those situations. So the first one we studied was linear factors. If we had a function, say 3x minus 4 over x plus 1, x minus 2, x plus 3, then we would break it up as a over x plus 1 plus b over x minus 2 plus c over x plus 3. So this one has just linear factors to the first powers. So each linear factor gets broken up into a single fraction, and the numerators are constants. All right, now I'm not going to solve for a, b, and c, but it's not such a big deal. I'll point something out here. We have this denominator is third degree. If you multiply this out, you would have x cubed plus a lot of other stuff. Third degree, polynomial, 3 letters. Okay. Now here's the next type of problem we had was like this. If I had x squared minus 2x plus 5 over x plus 2 squared, x minus 1 cubed. Now we have powers of linear factors, and let me go ahead and write it out, then we'll talk about it. So using x plus 2, I have a over x plus 2 plus b over x plus 2 squared. Then this one, x minus 1, I have plus c over x minus 1 plus d over x minus 1 squared plus e over x minus 1 to the third power. So in this case then we use the linear factors and we go first power, second power, as high as we need to get up to these powers here. So you can see what I got there. And it's going to take a bit of work because we have 5 letters to solve for. That means if we equated coefficients, we would have 5 equations with 5 letters, 5 unknowns. And those tend to be a bit more complicated. But notice this is a x squared term. This will give me an x squared term. This will give me an x cubed term. Altogether, this is a 5th degree polynomial. And look at that. 5 letters. 5th degree polynomial. Alright, now the third case, which I just did in the last video, is the irreducible quadratic form. So if I had something like x minus 4 over x squared plus 1 times x squared plus x plus 1. Either one of these can be factored, and but they're also quadratics, 2nd degree polynomials. So here's how we would split it up. For this one, I'll use ax plus b over x squared plus 1. And then over here, I'll use cx plus d over x squared plus x plus 1. So each one of these gets a linear polynomial on top of the irreducible quadratic. And so that's how we set those up. Notice again here, look what we have. This would be a 4th degree polynomial if we multiplied it out. Look at that, 4 letters. It works. Alright, so now this is a 4th case, which, oh boy, that'd be long. And I'll just alter this one. If this was squared, for example, then I also have to add in a 2nd power. So just going off of this would be ex plus f over x squared plus 1 to the 2nd power. So it's like the repeated powers situation. You have to use the first power and then the 2nd power for this term here. So that added into it a new polynomial. Now I've got x to the 4th times x squared. It's a 6th degree polynomial. And look at that. 6 letters. So these, as you might think, could get rather long. Alright, so those are the 4 cases this at least one textbook I'm looked at illustrates. There's some other problems that could come up though that are outside of this set that could possibly be worked with partial fractions or might not be. So I want to examine those in the next couple of videos. Kind of a short integral of x squared over x squared minus 1. What do you do? Well, one technique that would be natural here would be a secant substitution. In other words, you could turn this into a trigonometric substitution by letting x equal to secant theta, and that should work. That should work. But if we attempt this by partial fractions, let's see what happens. So bear with me here. I have x squared over x minus 1, x plus 1. So I went ahead and factored my x squared minus 1 and x squared. And then the natural way to split this up would be a over x minus 1 plus b over x plus 1. Now when we, there's my green pen. Okay, now when we clear the fractions on this, multiply everything by x minus 1, x plus 1, let's see what happens. I'm going to get, this will cancel. I have x squared equals to ax plus 1, a parentheses x plus 1 plus b parentheses x minus 1. So I forgot to put the square there. That's x squared. I can solve for a and b. I can solve for a and b. If I let x equal to negative 1, I've got 1 equals to 0, and then this will be minus 2b. So b is equal to negative 1/2. And then if x was equal to positive 1, in order to cancel this part, I get 1 equals to 2a. So a equals to positive 1/2. So a is 1/2, b is negative 1/2. That means I want to do some erasing. Okay, so let's see. Hang on here. Well, when I replace a and b and factor out to 1/2, that's what we get. So what's the problem with this? The problem is that the left side doesn't equal to the right side. Watch this. On the right side, if you were to combine your fractions, I get a common denominator of x minus 1, x plus 1, and up here I'm going to get x plus 1, and over there I'm going to get minus parentheses x minus 1. So I end up with 1/2 of the x's cancel, and I get a plus 2, 1 plus 2. I have a 2 over x minus 1, x plus 1, and that equals to 1 over, if I multiply it out, x squared minus 1. So, but you know what? I started with x squared over x squared minus 1, not 1 over x squared minus 1. So, big problem with that. So, now here, I'll show you where another place we might have caught this mistake. And so I need to go back to my partial fraction expansion again and do it the equating coefficients method. So we had a over x minus 1 plus b over x plus 1. Now if I clear the fractions, like I did before, x squared equals to a parentheses x plus 1 plus b parentheses x minus 1. And if you multiply out the right side, we have the coefficients of x will be a plus b. It's a plus b parentheses x. The constant coefficients will be a minus b. And over here, if you really think about it, this is x squared plus 0x plus 0. So I can put get a red colored pen here. I can 0x means a plus b must be 0. 0 over here means a minus b equals 0. And then what about x squared? I have nothing to match with it. I don't have a 1x squared on the right side. So, and in fact, if you solve this system, a plus b equals 0, a minus b equals 0, it's what we call a homogeneous system, has only a trivial solution. A and b both must be 0. And so this will literally tell us a and b are both 0, which means my fraction equals to zeros. Okay, so we see why it doesn't work. And now how do you spot these in advance? You know, how do you know you're going to run into one of these? You probably noticed the degree of my numerator is the same as the degree of the denominator. And when that happens, or if the numerator has a higher degree, if that's a higher degree, then we're not going to be able to use partial fractions on it directly. But believe it or not, we can use partial fractions here, but we have to do something else first. So, so again, one more time, that the problem is when your numerator polynomial has a higher degree than the denominator, or has the same degree, then the methods of partial fractions will not work without some adjustment. So I'll show you how we can adjust this one. So I'll erase this part of the board and we'll start fresh. So there is a way around this, and it involves using long division of polynomials. So I don't know where you are in your knowledge of long division, polynomials. I teach it in beginning algebra, and that's the last time we normally see it until differential equations. We get to use it with linear operator methods. All right, plus here, it shows up here. So if x squared is divided by x squared minus 1, how's that going to help us? And if it helps to see it, this is plus 0x plus 0. Alright, so x squared goes into x squared one time, and I multiply 1 times x squared minus 1. I'll line up my terms correctly. X squared is under x squareds, the minus 1 under the constant 0. And then we subtract this from here. And in beginning algebra, I'll say we change the signs and add. Same thing. The x squareds cancel, and I'm left with a 1, which means my remainder is 1. So this is 1 plus 1 over x squared minus 1. Alright, so that means I can split this integrand up into 2 parts. This is equal to 1 plus 1 over, I'm going to factor that, x minus 1, x plus 1, and dx. Alright, now here I can use partial fractions there. That'll work. I just have this extra 1 involved. Well, let's go ahead and finish this with partial fractions. I went ahead and did the partial fraction expansion. Actually, I kind of winged it, because I've done a lot of these. 1 over x minus 1, x plus 1 should equal to 1/2 times this this subtraction. So if you add these together, you would, on top you get x plus 1 minus x minus 1 over x minus 1, x plus 1. And then here the x's cancel, I get a plus 2. 1/2 times plus 2 is 1. So just to show you that it works, there's the partial fraction expansion. So therefore, we're integrating this one plus 1/2 times 1 over x minus 1, and then minus 1/2 times 1 over x plus 1 dx. So I took this part, expanded it, put it there. Don't forget the plus 1 over here. And now we can finish it. It'll be an easy finish. Let's see, I end up with x, integrate 1, you get x. I get, oops, it's not equal to, plus 1/2 natural log absolute value x minus 1 minus 1/2 absolute value, oops, natural log, there we go, natural log x plus 1. And then there's a constant over there. Let's see, let's combine that together. X plus 1/2 natural log of x minus 1 over x plus 1. Okay, let's see. So there you go. And you know, 1/2 natural log is the log of the square root. We could use that as well. and so on and so forth. So there we go. Matter of fact, let's see, you could, nah, I think I'll leave it at that. So it'd be interesting to compare this answer to what you would get if you use the trigonometric substitution. Is it going to work out to the same thing? And it's supposed to, if I did everything right. So, all right, well, we'll call it on this one, and then I want to next show you an integral that does not lend itself to partial fractions. Well, I'm going to set this one up for integration by doing the partial fraction expansion. The first thing we notice is that the denominator has higher degree than the numerator polynomial has higher degree than the denominator polynomial. So we can factor x squared minus 7x plus 12, so I have two linear factors, and that won't be so bad. But again, the numerator has a higher degree, or when it's equal to, we have to do long division first. So I wanted to show you how long division looks on one of these big ones. So let's see, I'm dividing this term, x squared minus 7x plus 12, into x to the third. Now I don't have an x squared here, so I'm going to put one in, plus 0x squared minus 4x plus 7. Alright. So here's my divisor, my dividend. And when we start these long divisions, we take the highest degree term dividing that highest degree term. So x squared divides into x to the third power, x times. So I'm going to put x here. And now I'm going to multiply x times my divisor. It gives me x cubed minus 7x squared plus 12x. At this point in arithmetic long division, we subtract this part, and but as I mentioned before, I teach this in beginning algebra. I tell them to change the signs and add, because otherwise, when you're subtracting with negatives, it gets easier to make a mistake. So if I change the signs and add, the x cubes cancel. I have a positive 7x squared, and then a negative 16x plus 7. Well, we have to do some more. Divide x squared into 7x squared. It goes 7 times, so plus 7. And I'll multiply 7 times this polynomial, 7x squared minus 49x plus 84. And then change the signs and add. Okay. So I have, see, 49 minus 16 is 33x, and then this will be plus 77. Well, all right, so this will end up being, okay, the integral of x plus 7, that's the whole part, and then here's my remainder. My remainder I'll write as, and by coincidence I can factor 11 out if we wanted to. I think I'll just write it 33x plus 77 over, and my denominator can be factored. It's x minus 3, x minus 4. And then it's, the whole thing is with respect to x. Alright, so we can split up this fraction into whole part, x plus 7, and then the remainder, 33x plus 77, goes on top. I factor the denominator. Alright, now from this point I don't think you would have a whole lot of trouble solving this by partial fractions. We have two linear terms, so we'll end up with two logarithms out of this part, and then we'll have x squared over 2 plus 7x, and then at the end we'll have a plus constant. So anyway, not too bad from there, but we had to do some preparation work here in order to get it ready for a partial fraction expansion. All right, so there's that, and now I want to go on to an example that we're not going to be able to. We're just not going to be able to integrate, but I want you to see why there's a problem with it. So here we have integral dx over x minus 1 times x cubed plus 3x minus 7. So I'm pretty sure this doesn't factor, and so I'm not going to worry about it. But you might say this is an irreducible cubic polynomial. We cannot factor it, but it's not quadratic, it's cubic. And I guess I want to demonstrate to you that I don't think we could do this with partial fractions. In fact, I don't think we can integrate this one at all. We would have to use a numerical technique to solve it. So bear with me here. Let's see if we can get this to work. All right, so this will be 1 over x minus 1, x cubed plus 3x minus 7 equals, so my first part will be a linear factor, so it's a over x minus 1 plus, now over here, again, we can't factor this. Let's go with a second degree polynomial on top. In other words, bx squared plus cx plus d over x to the third plus 3x minus 7. Okay, well, now will that work? Maybe, because this is a fourth degree polynomial over here, and I have 4 letters, so that seems to fit the pattern. And I believe we can solve for a, b, c, and d here. So let's go ahead and do that. If I multiply by this, clear the fractions, I have 1 equals a parentheses x cubed plus 3x minus 7 plus parentheses bx squared plus cx plus d times x minus 1. All right, so and that just looks like quite a mess. I think we can solve for a rather quickly if we let x equal to 1, because I'll have 1 here equals to 1 plus 3 minus 4 is what, negative 3a. I put 1 here, this is a 0, we don't care what that is. So a is negative 1/3. I'm going to write that up top here because I may need some room here. So that's taken care of. A is negative 1/3. All right, now if I knew the roots of this equation, I could plug it in, but I don't because it's not reducible. And I'm going to have to equate coefficients, so I'm going to multiply all this mess out. 1 equals to a x to the third plus 3ax minus 7a plus, see, bx to the third plus cx squared plus dx minus bx squared minus cx minus d. And let's see, we'll do some factoring here. The x cubed terms have a plus b as coefficients. So a plus b, x to the third. And the x squared terms are here, c minus b plus c minus b, x squared. And then the x term would be 3a, let's see, 3a plus d minus c times x. So I'm going to make sure I took care of everything here. I accounted for the x cubes, I accounted for the x squareds, and I accounted for the x terms, 3a plus d minus c. Okay. And then what I have left is a constant term plus negative 7a minus d. Negative 7a minus d. There we go. Okay. Now then, this will be 0 because I have 0x cubed over here. So let me plug in a 0. That's 0. That's 0. This is 0. And this is equal to 1. So I think we can solve for everything fairly quickly. A plus b equals to 0. Remember that b is negative 1/3, so a is negative 1/3, so b needs to cancel. B is positive 1/3. And then c minus b is equal to 0. Well, b is 1/3. So c will need to be the same thing. B and c are equal, so c needs to be 1/3. And then to get d, I could, well, I could go over here, 3a plus d minus c equals to 0. 3 times a would be -1 plus d minus c is 1/3 minus 1/3 equals to 0. So if I add those to the right side, I get 1 1/3 or 4/3. D is 4/3. D is 4/3. All right, so that's a little bit of work, but not too bad. I didn't think. Okay, well, I'm going to take all those coefficients and plug them back in and see if we can integrate. So I'll do some erasing first. I rewrote the integral, so from here down to here, all these have 3's in the denominator, so I factored 1/3 out of the entire integral, and which meant I had a over x minus 1 became actually -1 over x minus 1. And then this part here, ignoring the denominators, I have 1x squared. C was 1/3, so 1x squared plus 1x plus 4. And replacing it. Alright, so it's it looks somewhat doable. I mean, we sort of can integrate this part of it. There's where the problem is, because I don't know a way to solve this. I don't know if anybody does. Now, the reality is that we can't integrate every possible function. There's not an antiderivative that exists in the types of functions that we're accustomed to. You know, we work with, they're called elementary functions. We have polynomials, we have roots and radicals, we have fractions, rationals, we have trig functions, hyperbolic functions, logarithm, exponential functions. When you look at all these functions, they're called the elementary functions. Well, it turns out that not every antiderivative is composed or comprised of elementary functions. And why do I think this can't be integrated? Because I have no substitution method that's going to work. If I try ordinary u substitution, if u was equal to my denominator, x cubed plus 3x minus 7, then du will be 3x squared plus 3. And the numerator is x squared plus x plus 4. Now, this part is dx. This part here is a third of that. So actually I could substitute that out fairly easily, which means I would be left with 4 divided by this polynomial. And I don't know how to integrate 4 over x cubed plus 3x minus 7. I don't think there's a way to do it. So actually in this particular example, the problem becomes 4 over the cubic. Okay, that part actually we could do, but not that part. And so that's why we create numerical methods of integration, because we simply cannot get an antiderivative for everything. So anyway, so here's the bottom line with all this example. We had an irreducible cubic. It will be rare and unusual for us to be able to solve one of these which contains an irreducible cubic or higher degree polynomial. It will be very unusual, a fluke, if we could actually solve that by partial fraction expansion. And in this case, we could not. So I think we're pretty much out of luck when it comes to these integrals in general. And anyway, so I wanted to let you know that there is a limitation to partial fraction expansions. And so that's where we leave it there. Okay, now I want to do one more problem where it doesn't look like a partial fraction expansion, but it turns out to be. So one other example here. I wanted to do one last example, and you know, at a glance it does not look like a partial fraction expansion problem, but it turns out it is once we do do the right preparation work. Now, most of these problems I come up with are my own. I just make them up. But this one came out of a book, so I like to give credit for it. This came from Stewart, 7th edition, and it's on page, let's see, 517, number 39. So, okay, so anybody keeps track of those things. That's where I got this problem. It doesn't look all that original to me, but I like to give credit when credit is due. Okay, now then, what do you do? All right, we can't split up the square root of x plus 1 in any way. We could attempt to combine x with it, and this would end up being the square root of x plus 1 over x squared integral dx. And I don't think we can solve that either. It almost looks like a substitution would work, maybe, but when you get the, for example, if you let u equals to this, or u equal to that, I don't think it's going to work, because it's just not going to work at all. Alright, so what in the world do you do? Going to put a substitution here. I'm going to let u equal to the square root of x plus 1. And that might work because I can figure out what x is from that substitution. So if I square both sides, u squared equals to x plus 1, which means x equals to u squared minus 1. Alright, great. And so now I have a substitution for the numerator and one for the denominator, dx. Take the differential here, dx would be 2u du. So there's the differential of the right side. So let's put everything back in, and we ended up with u on top over u squared minus 1, and then on the side I have 2u du. So when you work that out, it's the integral, it's 2 times the integral of u squared over u squared minus 1 du. And do you recognize that one? I just did this a little whiles back in another video. And except they were x's, we had x squared over x squared minus 1. So by amazing coincidence, I managed to pick a problem out of Stewart, which turned into a problem I've already worked. So, and fortunately I wrote down everything for that problem. So I can read off the answer. 2 times the result I got earlier in terms of u's would be 2x plus natural log absolute value u minus 1 over u plus 1 plus a constant. Now it would be 2 times the constant, but 2 times the constant is still a constant. So I took the result from the earlier example and multiplied it by 2. And then to finish this problem, I need to substitute u back in. So we end up with 2 times x. So that's 2 parentheses u squared minus, oh, I got a mistake here, don't I? That's got to be u, doesn't it? 2u. Okay. Alright, let me try that again. Alright. So I copy that over, but I have to stay in u's. Alright, so 2 times u will be 2 times the square root of x plus 1 plus natural log absolute value. Alright, square root of x plus 1 minus 1 over square root of x plus 1 plus 1, and then plus a constant. So there you go. It's kind of a little bit ugly, isn't it? but that's the integral. So there are some examples where if you do a u substitution, it'll turn into an integration by parts. And I thought I would just do one of those, and I was kind of happy that we've already worked this one. So I was able to get to the answer fairly quickly. Okay, so that is what I know about partial fraction expansion. Happy expansion, and we'll see you in the next video.